Tree diagrams. That's what we're going to be talking about today. Tree diagrams is another way, another visual representation for to help you with probability, just like sample spaces and Venn diagrams are. Okay. So the best way to describe this is just go ahead and just dive right into an example. Okay. It says the probability that Samuel, a key member of the school's archery club, hits the bullseye is 0.8. Samuel takes 2 shots. Assume the success with each shot is independent from the previous shot. Meaning, because he makes the first one doesn't mean that he'll make the second one. Okay, they have their each instance when he steps up to shoot, the arrow does not depend on this previous shot. We're going to represent this information in a tree diagram. Okay, so when he steps up and he takes his first shot, he has 2 things that can happen, right? What are those 2 things that can happen if he steps up and fires the arrow?
You could hit a bullseye or you could not hit a bullseye.
Okay, and so that represents one of our branches in our tree diagram. Okay, so he steps up and he takes his first shot. Okay, because how many times does he shoot it? Twice. So he steps up, and 2 things can happen. He can either hit the bullseye, or he could miss the bullseye. What's the probability that he will hit the bullseye? 0.8. So 80% of the time. So 0.8. So if he doesn't hit the bullseye, what's that probability? 0.2. And this is the first branch in your tree diagram. That's how you represent it, okay? Each branch should add up to be 1 or 100%. Just like if you were doing, I don't know, say you had like a table breakdown of like different ones that should all add up to be 100% or 1. So he steps up, shoots, whatever happens, he picks up another arrow and he shoots again. Okay? What are his 2 possible outcomes there, or his possible outcomes there? The second shot. It's the same, hit or miss. Okay? Now, if he takes the first shot and he hits the bullseye, he's still going to shoot again. So he still has 2 different outcomes that can happen if he hits the bullseye or if he doesn't hit the bullseye. He can hit the bullseye again, or he can miss. Say he misses the first time. He's still going to step up and shoot it again. So he still has the same 2 outcomes. And just like before, our probabilities are going to go on our branches. What's the probability that he'll hit a bullseye? 0.8. That he'll miss. So again, 0.8 and 0.2. So what it means is independent from the previous shot. It has no effect. Has no effect. And this right here is our tree diagram to model the situation. If he took another shot, we would have again 2 more branches off of each one of these outcomes. Yes?
Does it matter which way it goes, or is it always the side?
Side usually saves the most space. Yes.
Is there a way to like conditional?
And you can definitely do conditional probabilities with tree diagrams. Now, one thing that I like to do when I have a tree diagram, you don't necessarily have to do it. However, it makes it a lot easier when it comes to answering questions, especially if you have an A, B, C, D, E option, is actually find out what are your possible outcomes, okay? And I like to put those off to the side. So, he takes 2 shots. He can hit a bullseye both times. To find the probability that hit a bullseye both times, you multiply both of those branches. Multiply 0.8 by 0.8, and what do we get? You will need a calculator. Point what? 0.64. So the probability of hitting a bullseye twice is 0.64. And all you do again to get those numbers, you just multiply along the branches.
Is that
Hmm?
independent?
I can hit the bullseye the first shot, but then miss the second shot. What's the probability of that happening? .16. I could miss the first time, but then hit the bullseye the second time. What's the probability for that? .16, again, you're just multiplying along the branches. Or he could step up and he could miss both times. What's the probability of that happening? Point what? 0.04. And the reason why I said, like I kind of knew that you guys were a little bit off because all four of these numbers should what? Add it to 1. So I'm already at about, 90.9, so it could have been 0.4. You see how it works? And so now this will help us when it comes down to answering these questions. For example, A, find the probability that he hits 2 bullseyes. We just found that out. What is it? 0.64. What's the probability that he hits only 1 bullseye? 0.32 or 32 of 100 because you have these two situations, don't you? He could hit it then miss or miss then hit. So you take both of those probabilities and you add them together. That's how you get the 0.32. Okay, because there are 2 instances where that can happen. And the last one, what's the probability that he hits at least 1 bullseye? 0.96. Very good, because he hits at least 1 means that he can hit on just 1 or both. So you would add up all those probabilities together. And think about it, if you have it nicely laid out, all you have to do is just keep referring back to them instead of trying to recalculate it every time. You see what I mean? Okay, so there you go. Tree diagrams, find out probabilities. Now we're going to look at that one that was on your homework, number 2. Okay? Because I put it in here. This is an example of a tree diagram. So if you don't have to write it back down, but you know where you can find it. So you might want to say number 2 from last night's homework or number 2 from conditional probabilities homework. So that way you don't have to write down this problem. Save some time. You can go back and write it later. In any given season, a soccer team plays 65% of their games home. When the team plays home, they win 83% of their games. When they play away from home, they win 26% of their games. The team plays 1 game, and we've got some questions they want us to address. This can very well be modeled with the tree diagram. What do you think the first branch is going to represent? Say again? If they play at home or not. So our first branch is going to be if they play home and if they play away. What's the probability that they play home? 65%. 0.65, 65 out of 100, 65%. I don't know how you want to represent this. 0.65. So if they play home 65% of the time, that means they play away 35% of the time. So there's the first branch of our tree diagram. Now if they play home, what could happen? They could win or lose. So I have 2 instances that could happen here. They could win or they could lose. Well, if they play home, what's the probability that they'll win? 83%. So then what's the probability that they play home, they lose? 17%. And again, each branch should add to be 1 or 100%. So they only give you one part of the branch. You can easily figure out the other by just subtracting it from 1 or 100. What if they play away? What are my outcomes? Win or lose. Now we are not taking consideration ties because I know that's possible in soccer folks, okay? So just take that out of the equation. They say nothing about ties, okay? If they did have something about ties, then you would have a third branch in there. Does everybody understand that? Okay. For those who know nothing about soccer, you could win, you could lose, but you could also tie. That's how the game's good. So, what's going to be on my win branch? 0.26, and on my lose branch? 0.74. I'm going to need them to up their away percentages, okay? Because that's kind of like you lose basically 3 out of 4 games every time you play away. Like you have no chance of winning. That's kind of low. Kind of low.
Must have like a hill or something.
All right, so let's look at all of our probabilities, okay? If they're home and then they win. What's that probability?
Oh,
You will need one here. So three significant figures, point,
5, 3, 5, 4.
5, 4.
540.
540.
What comes after the 9?
Necessary, 5.
5.
A 5, okay,
Is it necessary to put the 0 there?
yeah. Can you get that place over there? Yes?
Is there a way to prefer for it to be written if it was 84%? Or
Well, if they say probability, that's a decimal. If they say percentage, that's a percent. What about home and then they lose? What's that probability? 0.1, right? Okay. What if they play away and they win? What's that probability? Multiply along the branches. Remember, that's where these numbers are coming from. We're multiplying along the branches. 0.094. Is this three significant figures?
I got 0.91. Or 0.091.
Okay, so,
I did.
okay, 0.091. And the last one, if they play away and then they lose.
Oh, I see.
5.9? Okay, that's what I got too. Okay, so let's make sure we're multiplying correctly along those branches.
Oh.
Okay?
Did they ever ask us to do a non-calculated
If they do, they would give you some simpler numbers. Like maybe say they're like, I don't know, they might say, you know, you win 3 out of the 10 times, something like that. They could very well put this stuff.
Like the last one.
Yeah, like the last one. So, all right. Double check behind you guys. Being nervous.
The last one I put
All right.
7.75.
All right.
Still someone.
Okay, so now it says find the probability that the team wins the game. Find the probability if the team plays one game. Find the probability that the team wins the game. 0.091 plus 540 because they can either play home and win or they can play away and win. So you're gonna add both of those two outcomes together. So home win plus the away win is point what again? 631. And there's the probability the team wins the game. So if they play away or home, the probability of them winning is 0.631. Now it says if the team does not win the game, find the probability that the game was played at home. This right here is an example of conditional probability. Because it says if the team does not win, that's the condition. Okay, I'm not looking for overall whether they win or lose, home or away. I'm looking specifically at if they do not win the game. That is the condition. Find the probability that the game was played at home. So just to set it up so you guys can get the visual there, you're looking for the probability that they play at home and then they lose. That's what you're looking at, okay? So you're looking for the probability that they play home and lose, the intersection between that, and then the probability that they lose.
In these situations, what's the difference between the intersection of the two?
Isn't it
The intersection you're looking for just that one particular one versus the union. That means you're looking for all the times that they were home and all the times that all the times they lost. So, what is the probability that they played at home and they lost? What was that? 0.0 or 0.111? What's the probability that they lose? What's the probability they lose?
Yeah,
0.3.
0.37. because you wanna add this one and this one together. Cause the probability they lose, they can lose two different times, either home or away. So there is your probability. When we type that into our calculator, we get a number. What number is that? 0.3?
Yeah.
Not 1/3, but 30%. So, if the team does not win the game, 30% of the time, they're at home. It's not too bad. It'll be a little more persuasive. But there you go, that's how you use tree diagrams with conditional probability. Questions? Let's look at another one.
So how did the wording work? It does not win, fighting
Well, that's the thing, if they say, if something happens, given that something happens, that should signify conditional probability.
So losing was
So losing was the given.
Given is the same as
Here's one more, that's probably the last one we get to for today. And this is a good one to end on. So a bag contains 5 green and 6 red balls. If 2 balls are taken out successfully without replacement, we have to find the probability of these 2 different situations. Another example where we can use a tree diagram to model this. How many branches am I gonna have?
2.
You're gonna have 2. What's gonna be along those branches? Or what's gonna be the part that goes here? Green and red. Does it matter which one goes on top? No. It really matters where the probability is. And this basically represents our first pick, right? So pick one. When I reach in, what's the probability that I'll get a green ball? 5 out of 11, because there are 5 green balls and there are 11 balls total. How many reds? 6 out of 11. So when you reach in, you have 11 balls to choose from. You pick a ball out and you do not put it back. And then you go in and you pick again. When I pick again, what could be my outcomes? Green or red, just like before. But this time, it's out of 10. Because when I originally started with 11, I reached in on my first pick, I picked the ball out, and I did not put it back in, which meant that there were only 10 balls left. Okay? So here it's going to be out of 10. If I reach in the first time and pick out a green ball, and then I reach in again, what's the probability that I get a green ball? 4 out of 10. Because if I picked green the first time, I started with 5, I took one out, that leaves me with 4. If I pick green the first time, and I reach in again, what's the probability that I get a red one? 6. Because when I reached in, I grabbed a green one, not a red one, so there were still 6 red balls in there. Down here, I have the same outcome. I have green, and then I have red. And I still have 10 balls in there, don't I? Okay. If I reach in the first time, get a red ball. Pull it out, reach it again. What's the probability that I get a green ball? 5 out of 10. And then what about reaching in and I get a red for the second time?
5 out of 10.
5 out of 10. Do my branches add up to be 1? Yes. 10 out of 10 or 11 out of 11. So let's bang this out real quick. What's the probability that, no calculators here, what's the probability that I get green and green? 20 over, what is it? 110. Okay, we're gonna do this one without a calculator here. So you multiply straight across the branches. 5 times 4 is 20, 11 times 10 is 110. What if I reach in, get a green one and then a red one? 30 out of 110. What if I reach in, I get a red one first, then a green one? 30 out of 110. And then what if I reach in, I get a red both times? 30. Real quick, 30 plus 30 plus 30 plus 20 is 110, so we're good. 110 out of 110. Questions on where these numbers came from. So, at least one green. What's the probability that at least one green is chosen? 80 out of 110, because you would add green and red, and red and green together. So yes, your answer to A would be 80 out of 110. With it nice and neat off to the side, you don't have to go through each branch all over again. Then part B says, a red is picked on the first pick, given that at least one green is chosen. So this is conditional probability. If I wanted to set it up real fast, what's the order? What goes on the left side of the bar? Red is chosen, and then what goes on the other side? At least one green. Because that's the part that follows the given. So, I need the intersection between red and at least one green drawn. What's the probability that red and at least one green intersect? What's that?
Is that 30 out of 110?
60 out of 110.
You have to say red pick first.
Well,
If red is first.
yes, but we're looking at in the form of the formula for conditional probability. Remember, conditional probability is the intersection between red and at least one green
So it's like they took out one green.
over the probability that there was at least one green. So basically, I'm plugging it into the formula. I'm looking for the intersection between red and at least one green. And then I'm going to divide it by the probability that I get at least one green. And so then that'll take care of it being on, oh, I'm sorry. Pick first. Sorry. So you guys were right. 30. Sorry. All over what? What's the probability you get at least one green? 80 over 110, which you just found in part A. Keep, change, flip. My probability is 30 over 8. Which is 3 out of 8.